Dendrinal.
Dendrinal.
Dendrinal. Is that it? The automated dendritic cell production, production, which will be given by design team number 6. And it's Melanie, Robert, Jennifer, and Grant. Go ahead.
Are you? Should we just wait? All right. Whatever. Okay, so we are AutoCell Solutions, and we are here to kind of present today about our DendriNow system, which is automated dendritic cell production. Thank you guys all for coming out this afternoon. We appreciate it. Just to give a quick introduction, my name is Grant, and I'm the CTO.
My name is Melody, and I'm the CFO.
My name is Jennifer, I'm the CEO.
My name is Robert, and I'm the CSO.
And just to kind of give you a quick overview of what will be kind of covered in this presentation, this also will kind of be overlaid on the top of each slide going forward to just kind of keep you guys informed of where we are at with our presentation.
So, autologous cell therapy is a growing industry. Autologous cell therapy is a personalized cell therapy where cells are taken from a patient. They are altered to be often a vaccine, and they're then re-injected into the patient. This type of therapy has been very successful because it lowers the chance of the body having an immune response to the therapy. One example, in a trial for leukemia, caused remission in 100% of adults and 80 to 90% of children. Dendritic cells are the body's immunological memory. When an antigen is in the body, it's taken into the dendritic cell and broken down. Once it's broken down, it's then presented on the cell surface. T cells can then interact with dendritic cells and take the appropriate immune response. One interesting thing about dendritic cells is that they cannot replicate and therefore have proved many challenges during our cell culture scale-up process.
So the current cell generation process is composed of 11 different steps. So first you start out with your patient blood sample. Within those are the monocytes. Those are inoculated into the flask where they adhere to the polystyrene surface. The supernatant is then removed with any excess cells that were remaining, and then differentiation media is added. For 7 days, that culture is incubated. During that time, the monocytes differentiate into dendritic cells. The dendritic cells end up moving into the culture medium and into a suspension culture. At the end of 7 days, maturation media is added, so the dendritic cells become move from immature to mature cells. After that, they're incubated for a few more days, where then at the end of the 10-day period, they're harvested. So during the harvest, only the supernatant is collected, and that's what contains the dendritic cells. Right now, this process is done solely in a biosafety cabinet, done by trained operators. Therefore, there's a huge operator variability ranging anywhere from 1 to 10%. So what is our company striving to do? We're striving to not only optimize the dendritic cell generation process, but also to design an affordable, semi-disposable system to generate these cells. So in conjunction with Professor Murthy's lab here on campus, as well as funding from the Chemical Engineering Department, we were able to actually perform a series of experiments on campus during these previous 4 months. We decided to narrow in on 4 different parameters of the cell culture process, those being agitation, media addition, surface area, and monocyte adherence. The first 2 we really looked at were agitation and media addition. So agitation, seeing how agitating the culture flasks would help with the separation of the dendritic cells after they differentiate from the monocytes. The media addition, replenishing the media so that the cells are always getting new nutrients throughout the entire process. Surface area, looking at different flasks, different sizes, and with the main goal of seeing if we can increase that initial surface area that the monocytes have to adhere to so that we're retaining more of those monocytes before that supernatant is removed. And then monocyte adhesion being that traditionally these cultures have always been done as adherent cultures with the dendritic cells going into suspension. So we theorized maybe there's a better possible way to do it in terms of keeping the culture completely in a suspension during the entire process. So our first 2 experiments focused on agitation. The experimental flask underwent twice daily agitation sessions of 5 minutes for 50 RPM. At the end of the 7 days, the cells were analyzed using flow cytometry. From this, we were able to tell how many get a rough idea for how many dendritic cells were present in the supernatant, as well as the overall cell composition. From these results, we were able to conclude that agitation does increase the amount of dendritic cells that are produced. On average, we got about 66% more in the experimental flasks. The flow cytometry also showed us that the distribution and composition of cells within the media didn't change, and that there was no negative effects seen by adding that agitation. Then we looked at media addition. So ideally within our system, which we'll explain later, we wanted to incorporate continuous media addition. In the lab setting that we're in, that wasn't possible, but in order to replicate that, we decided to do daily media additions, keeping that end final volume of media the same. So based on the results that we got from the flow cytometry, we weren't able to make any conclusions about media addition, but we did show that it didn't have any negative effects. So then our last 2 parameters that we looked at, being surface area and monocyte adherence, we weren't able to do experiments in the lab, but we did do more research into literature to see if anyone had done previous experiments or ones that we could relate to our project. The first, for surface area, we were able to find a patent that is expired now, but they looked at using monocytes with microcarriers with the monocyte generation or dendritic cell generation procedure. They found that it actually increased the production of dendritic cells by 10-fold. They were not doing it in a flask, they were doing it in cell culture bags, but they did have a control. And then also looking at different types of cultures, we came across a paper that was recently published in the last couple years that used a roller bottle system. And they showed that there was no difference between the standard flask and this roller bottle system, which we'll explain a little bit later. So based on the experiments we did and all of our literature research, we decided to make certain modifications to our process and to implement into our final design. The big takeaways from this being we are changing from the T75 flask to a roller bottle system, where we are adding microcarriers to the flask as well as increasing the available surface area to those monocytes, as well as adding continuous agitation.
So kind of to roll into our second objective, which was the actual designing of a system, like an automated system capable of taking into these optimization results. So this is kind of introducing our cell culture system, which we've called the DendriNow system. And there's really 2 kind of primary components of this system. We have the skeleton system, which is kind of a standalone single purchase system that doesn't need replacement. And then we actually have like a disposable kit with a cell culture flask. So that's all kind of cell product contact material. So this is again for patient-specific samples. So one kit will work with one patient, and then you kind of throw out all that kit, and you just get another one to run another sample. So to go into a little bit more depth about the skeleton system alone. So again, this is kind of the main chamber of this device is an incubation space. What that means is we're trying to maintain certain environmental conditions within this area, those being 37 degrees Celsius, 5% carbon dioxide, and a relative humidity between 90 and 100%. Those are all pretty standard for an incubation space, especially for cell culture experiments. So our system does take that into account and actually continuously monitors those environmental conditions with our programmable logic controller, which is kind of right behind this HMI. So what that controller does is it takes the measurements into account, is able to adjust based on any measured disturbances, and then initiate some sort of system response to correct for those set points. So for instance, if you open the door and you let out some heat, the system will automatically be able to kind of run through the ladder logic that we've installed on these controllers and kind of initiate a response where we start heating up the temperature control unit to correct for that. So that's kind of how we're maintaining an environment that is really healthy for the cell culture like experiment going on. To kind of talk a little bit more on some other points, we have the media bag delivery system above. So those media bags will all be kind of prepped before this process begins, and then you kind of hook them up, and then you automate the system and you walk away. So it takes away a lot of that operator dependence and a lot of the time or labor-intensive requirements that the manual process had. But to keep going, also in the skeleton system included is 2 peristaltic pumps and 4 pinch valves. So those equipment, we originally thought of including that within the disposable kit, but that really made our disposable kit a little bit pricier than we wanted to. So we were actually able to find solutions that were non-product contact material, but able to drive flow in the same way. So they all kind of apply pressure to the tubing, but externally. So it's not coming in contact with the blood sample, and therefore it doesn't need to be replaced. So that's kind of how we kept our kit's costs down, and it was pretty cheap components to really add on, and we thought that was kind of the best solution for that going forward. And then kind of unique, so again, the cell culture flask that you see in this rendering, that is part of the disposable kit, but the stand itself that it comes on, that is part of the skeleton system, and that's what's really providing the rotation that we're talking about for this roller bottle system. And I'll go into kind of the rolling aspect of the cell culture flask in a couple slides. The disposable kit, again, this contains kind of all of your product contact materials. So that includes your media bags, all of the tubing with all the kind of associated connectors, whether they be the T connectors or the aseptic connections, the culture flask by itself, which the next slide is kind of dedicated to, and then the harvest bag. So all of that is kind of a single-use equipment, comes in a disposable kit, you toss it after the sample and get a new one to start again. And here's our cell culture flask that we kind of designed, and this is kind of a proprietary design that we came up with and then had created the modelings and renderings with some help in SolidWorks. But the cell culture flask itself, again, it's a roller bottle design, but we based it off of the volumetric capacity of the T75 cell culture flask. So those are kind of the traditional cell culture flasks used for benchtop experiments right now. So volumetrically, it's comparable, but we're actually able to use twice as much surface area because of like the rotary action of these roller bottles, because it is kind of tilting and able to use the sides. So we do get a lot more functional surface area, which is really important in terms of decreasing kind of that competition for adherence for the monocytes. So that's kind of our thought process going forward with that assumption. You can kind of see they have standard inlet and outlet ports. That's just connecting to the silicone tubing that comes with the disposable kit. And then we actually have a size exclusion filter in all of the cell culture flask. That's important because, as we mentioned, we are actually incorporating the idea of microcarriers to these bottles. So all of these will come preloaded with 1 gram of polystyrene beads. And that's, again, just to kind of increase surface area. Based on the literature we found, they were able to really get like significant more yield when using these microcarriers. So we kind of incorporated it that way. And the filter is just to make sure when harvesting that none of the beads are like kind of ending up in the harvest system. So this is kind of our simplified process. So again, the previous process was 11 manual steps. This one's a couple manual steps, but mostly automated. So your pre-build setup, that's kind of just placing the disposable kit within the skeleton system. That's prepping the media, prepping the cells from the patient. And then you start the inoculation step, which we kind of talked about. And that's kind of signals the start of the automation process. So once the media bags are all set, you kind of close the system, press a start button, and that will pump in the cells first and allow them to inoculate within the culture flask before initiating the differentiation and maturation phases, which again, kind of it's again similar format to the manual process, just all automated. So you will have the differentiation media added over the course of the first 7 days, and then the maturation media added over the last 1 to 3 days. When that process has been completed, the last automated step is really kind of just waiting for the operator to remove the harvest, or the collected cells within the harvest. So once that process is complete, we pump out the supernatant through the filter, and then we have it in a harvest bag that can then be removed from the system by the operator. And that's 7 to 10 days of work that an operator is free to work on whatever else they need to, and not being kind of paying attention to these cells. So it's a significant time saving in that regard. and then you kind of just initiate the post-run disassembly. So that's really just kind of removing all product contact material, disposing of it in proper hazardous waste, and then sanitizing the equipment just with like IPA or something of a similar nature. Really just to ensure that there's no contamination issues. But again, the closed system is all disposable, so we should be able to avoid many of those problems. And here's kind of just our flow diagram with our control scheme. This is kind of similar to what we've kind of shown in the rendering and the other diagram. But I do want to kind of stress the kind of environmental controls that we have here. So again, we're measuring the temperature, gas concentration, and humidity within the incubation space. And those are all kind of feeding electrical signals to the PLC, the controller, which is able to use our proprietary logic software that we're incorporating in all devices to initiate appropriate responses. So we have a temperature control unit if the system needs to be heated. We have a vaporizer if we need to add humidity to the system, or a CO2 pump. So we have CO2 inlet on the back of our system, and we can kind of initiate a response in that regard to get up to the 5% CO2 level in the incubation space.
So throughout our whole design process, we really wanted to keep in mind the manufacturability of our product. And so in order to do that, we made sure that all of the raw materials and parts we were using for our design, aside from our proprietary roller bottle, were off-the-shelf parts. We also plan to standardize the lengths of the tubing, so there are only 2 different lengths needed to build our tubing systems. Also, the sterile connectors are all symmetric, therefore they cannot be installed backwards in the system. We plan to use a pull system for our manufacturing process, so this means that when an order comes in, we then plan to manufacture the product. It will be single part flow throughout our plant, so that we reduce the amount of work in progress and increase our working capital. We plan to organize our plant in work cells. So these are going to be U-shaped cells where our product moves in a counterclockwise direction. This is because most operators are right-handed, and this way most of the work will be done with their dominant hand. It also helps the operator movements not interact with the raw material replenishment lines. We also plan at each workstation to have point-of-use storage, so all of the tools and raw materials necessary for the assembly steps will be available at the workstation. This will prevent waste of movement and time looking for things that are needed. Finally, the storage bins of the raw materials kept at the workstation, when they become empty, a signal or Kanban will be sent out that will begin the process of replenishing the supply to the bin, and also can signal for the need to reorder the raw materials. This helps promote the flow system that we're working towards in our plant.
And just as a kind of a quick note, our assembly facility, we do plan on locating it in the greater Boston area. And that just makes kind of logical sense because there's a lot of universities, hospitals, and companies, like it's a biotech hub in Boston. So it kind of makes sense to be located here, where a majority of our clients are probably going to be based out of doing their research here. So for location factors, that's kind of our selected place going forward.
So our target market is the cancer therapy market. It's currently at $100 billion globally and expected to be at $150 billion by 2018. Right now, there are so many people in the world affected by cancer, and we hope that our product will be able to allow different companies to bring to market cancer therapies. We just think that there is a desperate need for these right now. It also will be a profitable market. There are currently 700 ongoing trials involving dendritic cells. We hope to reach 10% of this market by our 5th year of production, meaning we hope to sell 70 skeleton systems after our 5th year. So there are 2 main devices that we see as competition right now. One of them is the quantum cell expansion system. This is being used for dendritic cell generation at the moment. The biggest downfall of this system is that it's very expensive. The skeleton system for this costs over $100,000, and the individual kits per patient cost $5,000. We also see the Clinimax Prodigy system as a potential competitor. It's currently not being used for dendritic cell generation, but we think that it could be altered to do so in the future, and we'll be keeping an eye on them as a competitor.
All right, so continuing on with the economic implications of our project. So we are primarily concerned with producing a skeleton system along with the disposable kit. And the following slide will just give a quick breakdown as to what the raw materials for these two different systems are. So we'll start off with the skeleton system here. So it just quickly lays out the component, the supplier, what the purpose of the material is, and in addition it breaks it down by price per unit and then how much it will actually cost. So roughly all the different materials that are going into our skeleton system will cost about $10,500. In addition to that, we will also be bundling a management software system with our skeleton system to automate the entire process. And then similarly, this just quickly outlines our disposable kit pricings. It's pretty much the same thing as the previous slide, and we expect this to be roughly $700, and both of these amounts are before any labor costs are included as well.
So our pricing plan was to sell our products at 4 times the cost of raw materials. This puts our skeleton system at $54,000 and our disposable kit at just under $3,000. We also plan to sell a yearly maintenance package at a fee of just under $3,000. On the right is our production model. So as I previously said, we want to reach 10% of our target market by our 5th year, which involves selling 70 skeleton systems in the first 5 years. We hope to sell an additional 100 skeleton systems in the subsequent 5 years. Now, for each skeleton system sold, we expect 25 kits to be needed in the first year. This would have the skeleton system running every other week, and then we expect that the system will be running continuously in subsequent years, and therefore needing 50 skeleton systems per year. So our economic evaluation and cumulative cash flow diagram with an initial investment of $2.5 million shows that we would break even in 6.4 years. Our return on investment is 90%, and our 10-year net present value with a 12% interest rate is $6.2 million. The internal rate of return was calculated at 26.1%.
And finally, continuing on with any regulatory requirements we need. Since we are producing the means to produce the therapy rather than the actual therapy itself, we do not need to seek any FDA approval for our device. Nonetheless, though, quality control is an essential component to this because it will eventually be used for cancer patients. And so, since we are purchasing all of our raw materials from different vendors, they will each have their own internal quality control standards. But anything that comes into our manufacturing plant will go through our own quality standards to kind of do a second check and to ensure that everything that comes into the plant meets proper specifications and there are no defects associated with anything that comes in. And in addition to that, anything that is released to a customer will undergo rigorous product release testing to ensure that there are no defects from the final material. And then, in addition to that, since we are going to be a startup, inventory is essential to our continued operation. We need to make sure that we always have the proper amount of material so that way the manufacturing never ceases and the customers can always be supplied with the necessary amount of material. And so what we intend to do for this is to implement a barcode scanning system so that anything that comes into our plant is scanned and then logged into a master computer system, which will then flag anything that needs to be replenished in the plant. Furthermore, we will also need clean rooms for our kit materials since this will involve product contact. What the FDA recommends for this is a ISO 7 style clean room. What this basically dictates is the lower the number, the cleaner the room is intended to be. So it will be a moderate clean room, but nonetheless it meets FDA specifications. And then finally, prior to anything that is released to a customer, it will undergo a terminal sterilization procedure, and this will be outsourced to a local company called Steris Isomedics. And then finally, moving into safety considerations, we are a assembly plant, so our employees will be working with various pieces of machinery, and it's essential that all of them are properly trained on the proper use of personal protective equipment. And this goes without saying. Anybody who's working on our floor prior to working on an individual basis will be properly trained on all the different materials and to understand what different safety standards need to be met. Building codes, we are again located in the Massachusetts area, so any codes that are outlined by the Massachusetts Department of Public Safety will be outlined. This goes for water codes, air ventilation, electrical codes, everything will be up to spec prior to any operation. And then again, regarding noise, so this goes back to the personal protective equipment. We are going to be an assembly plant, like I said before, and it's essential that, rather not essential, but the noise level may eventually get to levels that may be detrimental to the human ear. And so again, we will provide all of our employees with the proper protection equipment to make sure this is never an issue. And then lastly, environmental considerations. We're not really using any chemicals at our plant. The worst is likely going to be IPA. But all disposal everything that's disposable will be done according to the Research Conservation and the Recovery Act. And any other chemicals that we use will also be outlined as well. And then finally, shifting over to HAZOP. I'm not going to go through everything individually because it's all relatively similar in terms of maintaining all the standards. So I chose to touch upon the heater system and the CO2 pumps. This just comes down to proper maintenance is essential, ensuring that everything and that nothing can go wrong. And it's very important that anytime that the system has sensors located throughout to ensure that anything that does go wrong is immediately flagged to the user. And that way they can alter the system and to make sure that nothing goes wrong that's detrimental to the user. And especially regarding the CO2 pump, with this, the biggest concern is whether this leads to a pressure increase inside the incubator. And to ensure that this never happens, we're going to have a relief valve just to make sure that this is never the case and no rapid depressurization occurs. And then shifting over the MFMEA. Again, this is very similar to the HAZOP. This just comes down to why we are bundling a maintenance package, why we are going to sell a maintenance package in addition to our system itself. We plan on this for the system to be using for multiple years after purchase, and naturally wear and tear will occur over the course of these years. And so proper maintenance is essential to ensure that anything that does begin to go wrong is immediately accounted for and can immediately be repaired before the system breaks down, and that way the customer never is subject to any break in production.
So just to kind of summarize the presentation as a whole, so our two objectives going in were to optimize or at least could put forth an initial optimization effort for the dendritic cell generation procedure, and we believe we were actually very successful in that regard. I mean, we've kind of shown the infancy of the process itself, because just by changing one parameter with agitation, we were able to increase the dendritic cell yield by 66%, and that's a very large number, especially in terms of dendritic cells, because they don't replicate. So it's like very important to really kind of maximize your yield and make sure that you're getting the most, especially for a patient like dosage. So that's like, we're really happy about that. And that's something that Dr. Murthy, whose lab we were working in, that's something that he can incorporate in his future work, because that will allow him to produce significantly more dendritic cells per run, and any experiments kind of generated from those dendritic cells, you have more to work with and you're able to get more work done with that. So we're very proud of kind of our accomplishments in that objective. And going with our other objective, the black box system, while it was kind of a preliminary design, we weren't able to ever create like a working prototype. We were very kind of satisfied with the level of design we put in, what the components that went in. We think it was kind of a well thought out system, and right now, like at the price point in the current market, it's very competitive with existing systems. So we believe that it is like a viable option, and we will kind of go into recommendations on the next slide to kind of how you further improve that. But I mean, and looking just at a project from like an economic evaluation standpoint, not only is this project feasible in terms of like the economic analysis that we performed, but it's actually a profitable like excursion, which is kind of speaks to the need for cancer vaccinations in this day and age. But also it's a viable business opportunity moving forward. So for instance, we had with a $2.5 million initial investment, which is relatively standard for smaller biotech companies in the area. I know companies like Quad Technologies have worked off of a similar initial investment. So with that kind of initial investment, we're able to pay that off in 6.5 years, and by the end of 10 years, have an internal rate of return of 26.1%. And a net present value of $6.2 million. So from those financial models, we do believe that this is a viable option and actually like something worth continuing to look into. And on that note, we actually have filed for a provisional patent through Northeastern. It's actually currently under legal review through the process. So we're really kind of excited to see how that pans out. And it's something that like Dr. Murthy going forward might utilize the patent or have to lease it out, I mean that's still in the future, but it's something that we're kind of really proud to say we've accomplished in these 4 months. But recommendations just going forward quickly. I mean we kind of showed the infancy in terms of the optimization. So we'd really love to kind of have additional opportunities to explore how we can better or produce dendritic cells at a higher yield. So, for instance, we only tried one agitation setting. We could fine tune that further and try longer periods of agitation, lower RPMs, and just see really what is maximizing your yield. Because again, I sound like a broken record here, but with a culture that doesn't replicate, you need to maximize your yield to make any sense with scaling up this process. So that's something we're like really, we'd be excited to continue. We also, while we're incorporating the polystyrene microcarriers, we never actually physically tested that. And that's something that, like, going forward, we would have loved to have kind of enough time to do that. But regrettably, kind of the 4-month period didn't allow for that. But again, we are happy with the level of progress we achieved. We would also kind of start rapid prototyping our system. 3D printers are a phenomenal resource for companies in the early stages, just to not only kind of get like a spatial awareness of the system like right now with the current dimensions, but just to start like essentially transitioning to a working model. So that's kind of like the natural progression for a system like this. Market research is something that we are kind of lacking, and that's something that going forward I would really kind of put more of an effort into, because we could reach out to laboratories or research institutions who are currently kind of looking into dendritic cells and get a better idea of not only kind of what their problems are with the current methods. I know we've talked about like the time and labor intensity, but see kind of like what else we didn't consider from their perspective, and then see how we can incorporate that further into our design. And then also use that research as a tool to say, kind of like, better establish a price point and also a method of purchase. So right now we're kind of selling the skeleton system as like a one-time purchase, but maybe we could get twice as many users if we lease it out or implement some kind of payment plan. So that's something that we would consider moving forward, and just to see if we did pick kind of the optimal solution and see how we could progress. Because I do believe that we kind of went with a conservative production schedule, and we were still kind of a viable company option. So I think if we were able to even increase our user base further, it'd be kind of a great way to achieve growth even more rapidly. And finally, just kind of expanding the scope of the system in general. So we talked about the Clinimax Prodigy system. That's currently used for T cells, and we're kind of concerned about them as competitors in terms of them adapting the system for dendritic cells. But we could always consider going vice versa in like the long distance future, where we have a system that is now functioning for dendritic cells, but maybe we need to kind of spin off and go more into T cells or something in that regard. So just kind of seeing what the scope is, getting kind of an idea of do kind of a litmus test of the market and just see like what is, how we could apply our system to other directions. So that's kind of our recommendations going forward.
And to finally close things out, we'd like to thank you all for coming to our presentation, and we'd just like to extend our gratitude to everybody who helped us throughout this entire project. Dr. Murthy for introducing us to the topic, and for allowing us to work in his lab, and for meeting with him on a weekly basis to kind of lay out the path we wanted to take with this. Zeke for his industry expertise. When we first met you, we honestly didn't know we were going to go with the project, but helping you out was, having you along the line, it narrowed our path, and it really helped us kind of figure out where we wanted to go. Ken Rapp for helping us for providing us input on what it takes for a startup what it takes to be a proper startup, and for investors to see in a startup to actually invest in them. And then Phil Soucy for helping us out with the SolidWorks drawings. They would have been very, very difficult had it not been for his assistance. And then Dr. Webster, Dr. Shi, and the entire department for the continued feedback and the funding that we received for this project. And I would like to open up the floor for any questions.
And thank you, by the way.
Thanks.
Very nice. Questions?
How are you going to control the dissolved gases in the bottle, in the glue bottle?
So I guess kind of standard to cell culture, and maybe you guys are better suited for this question, so if my response is inadequate, feel free to jump in. But we have kind of a built-in vent for the roller bottle itself, very similar to the T75 culture flask. And what that does is just allow for kind of constant gas exchange. And just, again, we kind of based off of similar designs to existing culture flasks, and that's my idea of it. I don't know.
Yes, if you go back to the.
So you're just controlling the temperature,
Just
you're
the-
controlling
yeah,
just the gas. in
just the
chamber.
gas exchange in the chamber.
The environmental conditions are pretty standard for cell culture work, and just allowing the filter for gas exchange is generally suitable, at least it has been for other cell culture flask designs.
We had looked into disposable probes and things, but one of our big goals was to keep our costs low, and we found that this was one of the best ways to keep that cost down.
Yeah, that's great. And then how do you see the potential for scale up? Say you had someone who, wouldn't go necessarily with your business because they need 100 of these, right? They're probably not going to buy 100 units.
Yeah.
Do you have any ideas around a larger unit
Yeah, so I guess we're really kind of trying to keep the theme of a single patient use, going back to kind of the autologous vaccinations. That's all patient specific, and that's something that we're kind of really want to stick with. We could look into an expanded option in the sense of having kind of one incubation space in multiple different chambers, but we'd have to look into kind of like the risks of contamination running that way. But we did kind of think about an idea where if we're kind of like leasing or selling our equipment to a company and having some kind of loyalty agreement in place where if they do decide to, because that's the jackpot for us, if a company actually is able to, using our technology, use these dendritic cells for vaccination purpose and then takes it to market, that's kind of like the home run for us. So ideally we'd have some kind of agreement in place where if they want to scale up, we'd like partner with them to kind of scale up that process with them and really kind of hold their hand throughout that process and make it so from their standpoint it's commercially viable to produce as many cells as they need to. So those are kind of our different perspectives on that issue. I don't know if that kind of answers.
Yeah, thank you.
I mean, there really are a lot of customers, right, that you
Yes.
could go after.
Yes.
You know, you're probably familiar with ATCC, the American Type Culture Collection, that sells S to C for probably everybody in this building who does research, as well as MUGAR and other places on campus. And they get biological samples from real patients. So to have processes that can optimize cell yield, and then they in turn sell it to other people is critically important. My question was going back to the preliminary studies, which I thought was a great part of what you guys did in your project. Did anything surprise you? I mean, was it, a lot of times in these biological studies, there are things that I find that you would expect, right, agitation to help with yield, right? I think as an engineer, as a chemical engineer, we would kind of expect that, and I think a lot of times we're surprised that people aren't already doing it. And I think what you did was you took something like that and turned it into a real idea and how you could actually have a device to help with agitation. But did anything else, you know, the media addition, the other parameters, did that surprise you that they didn't help or that they did help?
I think the media addition did for us, and with a few of us have some cell culture experience from Genzyme. They're using CHO cells. Obviously, they replicate, they're growing, but in that case, you need to be replenishing the media in order for the cells to be viable. In this case, it seems to be that the media addition every 2 to 3 days is sufficient for these cells to keep that high viability.
I think it would be interesting to combine the agitation with the media addition to see if by adding the media and having the media moving over the cells would make more of a difference, because when we did the media addition experiment, the samples were not agitated. And combining them, we think, might also cause a greater effect.
Absolutely. You know, you would almost think too, as an engineer, is there a way to develop an equation around this?
Right.
You know, and you tweak certain parameters and come up with the ones that are the most important.
We do a
in
DOE
terms of-
study.
Yeah. Yeah.
Yeah, we were kind of going into it. We did run into some complications in the actual lab setting where we had, like, our first experiment was kind of voided due to contamination issues.
Yeah.
So we were kind of a little bit, it would have been really nice to kind of go through, like we went into it with kind of experimental designs for all 4 of these parameters. Like we went in and really kind of designed different ways to test all of these. And then, we're kind of limited in both kind of the cell count that we were working with, which made it difficult to really split up into enough samples to like test all these parameters. And then also kind of some issues on top of that. But we are, again, we're really happy that we were able to actually prove something was able to help.
It's incredible, you know, and I know you guys are graduating, but you should think about the AICHE conference next year in San Francisco. And the department would be happy to help out if you wanted to submit something based on this work.
No, we'll see. I mean,
Awesome.
again, we've got the provisional patent in
Yeah.
review, so hopefully like that comes through and we should see how it goes from there. But yeah.
Excellent. Any last questions? It was great.
Thank you.
Thank you.